very excited to see so many participants, both online and in attendance, and I'm honored to introduce our invited speaker, Professor Victor Pambuccian from Arizona State University. Victor Pambuccian works in the area of foundational geometry, and he is known for his research on the axiomatic of geometries, such as affine, projective, Euclidean, ordered, equiaffine, hyperbolic, and the geometry of metric planes. Pambuccian interests focus also on definability questions in several geometries, including Minkowski space, and on reverse geometry. And he is author of many important publications on these research topics, on which he shed light on important issues. Currently, Professor Pambuccian is a visiting professor at the University of Urbino, where he will give a series of 10 lectures on the foundation of geometry. Today's lecture is the first in the series and it is entitled A Review of the Aims and Objectives of the Axiomatic Foundation of Geometry from Past to the Present. Before giving the floor to Victor, I would like to remind you just some practical information, just the house rules. Please switch off your microphone. Only the speaker will have the microphone active, and this is obviously to avoid confusion during the talk. Second, the dubbed and clarificatory questions are allowed during the talk. If you have one, please write in the chat. And structured questions and theoretical discussions are left for Q&A session that is programmed at the end of each lecture. Well, without further ado, please join me in welcoming Professor Victor Pambuccian. And please, Victor, you have the floor.
Is this connected? Is this visible now?
No.
No?
We need to.
Oh, okay. Okay. Sure.
Yes.
I have to go to the tricks of no.
Yes.
Let's see if I still know how to do that. No. Let's see. Here, vista.
Yes.
Yes. Modalità di lettura.
Yeah.
Good. Okay. Is this now visible on everyone's screen? Okay, good. So, thank you for inviting me, Pierluigi, and everyone in the department. I'll talk about several issues in the foundations of geometry. And this is an introduction to what I see as the history of this endeavor. In fact, I thought of writing this history about 25 years ago, and I'm in my 4th sabbatical to do so. During the other ones, there were just chapters that came out as survey papers or so. So I spent a lot of time thinking about these issues. But obviously, in presenting this, I cannot do justice to everything that has been written, because there's about my bibliography in the book, which is kind of the one thing I have, contains about 1,600 papers and books. So with the best of intentions, I couldn't tell you what's in each of them. So I'm going to just look at the main lines of development, and in the end, at some sociology of this field. In other words, how does it stand inside the mathematical village? How is it seen by other mathematicians, logicians, and so on? and what changes did occur. So let's start with the beginnings. The beginnings of this are with the publication by Moritz Pasch in 1882 of his Vorlesungen über neuere Geometrie. He had started writing it in 1873. And why does it start something dramatically new is hard to, well, there are some novelties there. One of it is to try to describe it would be impossible, because understanding even today what's inside means that you are already an expert in projective geometry. So this is not a book that can be read by regular mathematicians and made sense of. For example, as a contrast, the Grundlagen der Geometrie by Gilbert is something that myself as a 10th grade student got from participating in the Bundeswettbewerb Mathematik, the West German Mathematical Olympiad, and I could read it without any problem. If I had gotten the Vorlesungen, I couldn't make sense of more than the first 2 chapters. It's incomprehensible unless you actually know the stuff. So the first 2 chapters, though, do something revolutionary already. Namely, they realize that something was missing in geometry, which was order. And Pasch introduces order for the first time, recognizes the need to do so, and introduces it. And in fact, there are problems raised from order that are not solved today. This will be part of another talk about the Pasch axiom. So the significance why it is a break with the past is that Pasch sees geometry as it needs to become, in a certain sense, exact. That you cannot rely on a picture or on your intuition or anything. When it's done, it has to be purely symbolic. And here you have a quotation from him. And he says that the process of inferring must be everywhere independent of the sense of geometrical concepts, just as it must be independent of figures. It is only relations between geometrical concepts that should be taken into account in the propositions and definitions that are dealt with. In the course of the deduction, it is certainly legitimate and useful, though by no means necessary, to think of the meaning of the geometrical concepts involved. In fact, if it is necessary so to think, the gappiness of the deduction and the insufficiency of the means of proof is thereby revealed, unless it is possible to remove the gaps by modifying the reasoning used. So this shows us that this is really dramatically important. Now, is this absolutely new? No, but it's absolutely new carried out. There were people before, for example, Lambert said something similar in 1786, but he didn't carry it out. No. He said that it can and must be required that one nowhere in a proof call on the thing itself, but that the proof should be carried forward symbolically throughout, if this is possible. In this aspect, Euclid's postulates are the same as so many algebraic equations which one has before oneself, and from which x, y, z, etc. will be brought out without one's looking back at the thing itself. Now, what happened afterwards? So after this 1882, After 1882, there is this Italian intermezzo. We have Giuseppe Peano that takes it up. And what does he do with it? Well, in Pasch's case, everything was two-dimensional for his ordered axioms. And Peano did this at n-dimensional or regardless of dimension geometry. What do you do there to introduce order? Then we have Bailati, who does again order things, Veronese, who did something really remarkable, namely he discovered that the Archimedean axiom was actually necessary, that the Greeks were pretty wise in that, because you don't get it out of nothing. And then we have the most insistent of them, Mario Pieri, who produced axiom systems for almost everything. Projective geometry, inversive geometry, which is Möbius geometry, and Euclidean geometry between 1895 and 99, and then continued on to do even more. So clearly by productivity, he is completely different from all the others. The amount of things that he did. Now, a characteristic feature of these, which was not in Pasch, is the use of formal logic for the expression of the axioms and for the deduction. Next comes Hermann Wiener in 1890, who stated without proof, I mean, all of this thing has a prehistory, obviously. And in the prehistory, there are two giants, Jakob Steiner and Christian von Staudt, who put or tried to put projective geometry on a really geometric basis. What does that mean? Well, all of geometry came soiled, I would say, with a continuum, with a real number somewhere hidden. And these people realize that this is something ungeometric, that one should remove this dirt. And they almost succeeded. In fact, von Staudt almost succeeded. He had just one place where there was some continuity consideration. So in 1890, Wiener states without proof that one can prove the fundamental theorem of projective geometry from the trivial plane projective incidence axioms, which just say that, well, any two lines are joined by exactly, any 2 points are joined by exactly one line. Any two lines have exactly 1 point in common. I mean, any two distinct lines. Yeah. And every line contains 3 points, and there are 4 points which are in no way, collinear. So that's the trivial incidence axiom. So that if you want to get this fundamental theorem of projective geometry, all you need to add to this trivial stuff is the projective form of Pappus and Desargues. The novelty consists in the fact that for the first time, you could get it without any kind of continuity. Everything that I just said are purely incident statements. They have nothing to do with stating that the line is full of stuff and who knows what. So this claim was first proved by Friedrich Schur in 1899. By the way, both Pasch and Schur were Jews. I mean, Schur, his family had converted to Christianity, which wouldn't have been of great help, but both had the inspiration to die before 1933. Moritz Pasch in 1932 and Friedrich Schur in 1930. So they escaped what was to come. So here is what Pappus and Pascal, and Pappus is also called Pascal in the German literature. I mean, Gilbert likes to call him Pascal, which says what you see on the picture, that if you have two lines, the line of the P's and the line of the Q's, and you join the P's with the Q's as shown in here, then the three intersection points are collinear, as shown by that dotted line. This was something that was known by Pappus of Alexandria. It's probably the thing that took longest to figure out what is it good for. Now we know that we're telling our students that Apollonius studied the conics, but it was only with Kepler that we had an actual use for them. Well, this took even longer. It took to the 20th century to see what this thing is good for. And then we have Desargues, which is a later invention by the architect Desargues, which says that if you have three lines, you know, C1, C2, C3 that meet in a point C, and you have two triangles on these C's, the triangles are the A1, A2, A3, B1, B2, B3, then these lines of the A and B triangles intersect in 3 points there. And the dotted line tells you that those 3 points are collinear. So it's one of these configuration theorems that you're given something and then miraculously something else also happens. Okay, what is the fundamental theorem of projective geometry? Well, it's something about projectivities. And for this, you need to define what the perspectivity is. And the perspectivity is this: if you have two lines, L and M, they had a point outside of it, you can establish a correspondence from one to the other by joining the P with the points on the one line and intersecting them with the second. So this kind of correspondence, this kind of map, is called a perspectivity. And the composition of a finite number of such perspectivities is called a projectivity. And the fundamental theorem of projective geometry says that a projectivity from a line onto itself that has 3 fixed points is the identity. Why this is important is something complex in projective geometry. Now, Pasch, although being so revolutionary in geometry with his view that everything has to be gapless, has a peculiarity. Namely, he was an empiricist of the Aristotelian type. I mean, you can't talk about the whole line because the whole line doesn't exist. There are only segments, and the segments can be extended. But there is no complete line, which you would find unusual in his time. But he isn't the only one who is revolutionary in one thing and rather non-revolutionary in other things. We have Copernicus, who was very revolutionary in one sense, but in the other, he's kind of a medieval astronomer because he thinks that the fixed stars are on a glass sphere. What about Frege, who is very revolutionary with his symbolic logic, but thinks that axioms have to be true, whatever that means. I think they have to be written on some tablets in Mount Sinai. So anyway, we got this thing. So next comes Gilbert and his Grundlagen der Geometrie. Now, although this work is apparently about the gapless axiomatization of three-dimensional Euclidean geometry, and Gilbert wanted to be kind of a modern Euclid, so he's interested apparently in this work to characterize a unique model. So three-dimensional Euclidean geometry over the reals, this kind of standard thing. the main trends in the foundations of geometry will not be the characterization of a unique structure. And this changes very shortly, even in Gilbert's own work. First of all, he tells us in the lectures on the foundation, because before publishing this, for about 6-7 years, he held lectures on this subject. And they have been published, there's a thick yellow volume of them, and you can go through them. It's a very assiduous work done by Michael Hallett, Ulrich Meyer, and so on. So he tells them there that the task of any mature science is to show how to introduce number. So what he tells us there is that the task of the axiomatic foundations of geometry is to show some connection to algebraic quantities, but without introducing them explicitly. So the story should be purely geometric, and you should be able to define inside that theory something that looks like magnitudes that can be added, multiplied, or whatever they can be in there. Okay? So that's the direction in which things will move, not to the characterization of this unique structure. This he shows by his next important paper, in which he tells us what is elementary hyperbolic geometry. This is in 1903, so very shortly afterwards. So what he does is he introduces a certain hyperbolic parallel axiom to his axiom system of absolute geometry and shows that every model of this is isomorphic to a certain Beltrami-Cayley-Klein model of over some Euclidean ordered field. So that all Euclidean ordered fields can show up as coordinatizing structures for this. So here he got rid of the real numbers, which is unusual because you would think, but until then, wasn't hyperbolic geometry filled with those hyperbolic sinus and cosinus that have something to do with e to whatever? I mean, what are you going to do with those? And how can it be elementary? Well, it is. So now you see that one aim of the axiomatic foundation of geometry will be to discover the purely elementary geometric content of these theories that came historically in this real numbers garb. They're dressed in real numbers, but the real numbers are red herrings. You can get rid of them, but it's hard. It's not easy. And if you can't get rid of it, then your question is that really geometry? So, or is it elementary geometry? So, this is a stark departure from what he apparently was doing in the Grundlagen der Geometrie. I say apparently because the Grundlagen der Geometrie is filled with other stuff, with Desargues and Pappus, and he clearly shows he's interested in a certain similarity between geometry and algebra. So one of the goals then will be this: look at the geometries that were already developed in the 19th century and find their elementary nucleus. Now, what's wrong with the real numbers, you would say? I mean, don't all famous mathematicians believe in them and they do fine with them? Aren't they supposed to be modeling outside reality, and isn't geometry about outside reality? And isn't reality continuous? Well, even in 1898, Gilbert knew that this is a fairy tale. He says a homogeneous continuum that would allow infinite divisibility and would thus achieve the infinitely small cannot be encountered anywhere in nature. The infinite divisibility of the continuum is an operation existing only in thought, only an idea, which is refuted by our observations of nature and by the experience drawn from physics and chemistry. In other words, he knew about the granular structure of space-time, that there are quanta of space and quanta of time. So this story about the beautiful real numbers that we should invite because they're out there in nature is total nonsense. They may be in our mind because our mind believes in this continuous, but they're refuted by the outside world. So that argument doesn't work. Obviously, in the meantime, we have much deeper reasons to discard that hypothesis of continuity than Hilbert had in 1898. So, for example, quantum gravity and all these quantum things that show that you can't think of continuity in any sense of being out there. Moreover, if you want to, so this is the point of why are the real numbers bad from nature. There are logical reasons why they're bad. Why? Because they depend on set theory, and set theory is a total disaster. So you don't want to invite that into geometry. You don't want to depend on set theory. You think that our geometric intuition or the geometry itself isn't dependent on the most monstrous thing that we stumbled into. And the real numbers depend on that monstrosity. And if you want that, then you have to import all the things about inaccessible cardinals and what axioms are you going to accept. And it's total nonsense. So from a foundational point of view, one shouldn't go that way. Moreover, if you want to really do it elementarily, if you want to follow this Greek model of, nice axioms about simple things that behave this way with each other, and to get a geometry, then that thing can never describe a unique model unless it's just a finite toy. So if it is an infinite thing, by the Löwenheim-Schulen theorem, it cannot be categorical. So there are all these reasons why we should stay very far from the real numbers in the first order axiomatization of geometry. Obviously, in 1899, first order didn't exist, but in the 1920s, it became clear that that's where axiomatization serious axiomatization happen. The rest makes no sense. So the first task, if you see that Euclidean was already done and hyperbolic is done, was to think of another geometry of constant curvature, elliptic geometry, which was done. Second, you can think about all of these cycle geometries, Möbius, Laguerre, Minkowski, Lie. That was done as well. What's Möbius? Möbius is an incidence theory about lines that are lines of the real plane to which you've added a potato that you write infinity. So the potato is on every line, and there are circles, the usual circles, and to the circles there is also the lines together with infinity. So the lines together with infinity and the circles are the new circles of this geometry, right? So you can think of the lines together with the potato as being circles of infinite radius. And then there are the points. And the theories about incidence between these points and these generalized circles. This was done. So how do you get the real numbers out of this and get, you know, a nice theory? Yeah, done. Again, Laguerre, what is? Here you have spheres. In other words, lines that have a direction on them. There is a parallel notion among these. So these are parallel. And then there are circles which have an orientation. And then there is tangency of the spheres, with these circles that are oriented, and the orientation must be the same to call the thing tangent. And then the points are also called circles. They're circles of radius 0. And then again, you're looking at this, you know, tangency thing. Was this axiomatized? Yes. And then again, I'm not going to go into what Minkowski and Lees, but everything was done. The Möbius and Laguerre was solved by van der Waden and Smith in 35, and a certain configuration theorem for circles, the Michael configuration, plays the role of pathos. Yeah? So once that is working, once your geometry satisfies that configuration of circles, then you have commutative fields and everything is going fine, just like you have in, yes?
The same historical geometry.
Sorry? Yeah, the same person, yes. The same with algebraic and the history of geometry, yes. Yes, we're going to go over that in a while. Significant contributions in this area come first and foremost by Walter Benz, also Mario Pieri, Roberto Permuti, Adriano Barlotti, Helmut Meurer, Günther Ewald, Lech Dubikaitis, Andrea Brunk, and Karl Strambach are among the contributors to this theory. Then come the Cayley-Klein geometries. So these are all old business. I mean, stuff that the 19th century gave us that we have to cleanse of the real numbers. And what are these? Well, Cayley and Klein realized that both Euclidean and hyperbolic geometry are parts of projective geometry in which there is a certain choice of something that's called an absolute. Absolute being the kind of the end of the world. And in the Euclidean case, the end of the world is your line at infinity. In the hyperbolic case, it's the interior of it's the end of the world is the circumference of a conic section. In the Beltrami-Klein model, it's just the perimeter of this circle. And the question was, well, you can take other things, other absolutes, and get other geometries. In fact, there are 9 such, which all have names. I mean, besides these classical ones, Euclidean, hyperbolic, and elliptic, there is co-Euclidean, Galilean, co-Minkowskian, co-hyperbolic, Minkowskian, doubly hyperbolic. These were axiomatized in terms of reflections by Rolf Struve in 2016. Polar geometries, which have something to do with a polarity. So you're given a higher dimensional projective space, and you call sets that are preserved by a polarity, polarity being a transformation that moves points to hyperplanes and hyperplanes to points, and that has order 2. In other words, if you do sigma squared, you get the identity. If you do sigma composed with sigma, you get the identity. And so this is a polarity. And you call a set strictly polar if it is preserved under this. And you're interested in certain subsets that are of maximal rank at least 3. and you get the so-called polar geometry. This was axiomatized in 1959 by Ferdinand Feldkamp, and then Cohen and Schuld extended the whole thing to the affine realm in 1990. This can also be said to be 19th century because, you know, polarities were known then and projective spaces were known then. So now the 20th century wasn't only busy in trying to create a purely geometric face to these 19th century geometries. There were also new geometries that appeared in the 20th century, although they're much less known except for, you know, one of them. First and foremost, there is Minkowski spacetime, which didn't exist in the 19th century. And this was first axiomatized by Robb in 1913. And then there were several additional axiomatizations by James Axe in 1978, and then by Ondrejka, Modoros, Székely, and Nemeti in the 2000s all the way to today. There is an enormous work they have produced, and they have succeeded in axiomatizing in the first order even general relativity, which sounds impossible because isn't general relativity some kind of differential geometry, and how can you do differential geometry in first order theory? Well, with an enormous amount of effort and many pages, you can get there. Now, there was also another geometry discovered by Karl Strambach in 1968 as a topological geometry in the style of Salzmann. Krzysztof Kraszmowski succeeded in 1989 to find a first order axiomatization for it. Now, the geometries that were referred earlier started as existing over the real numbers, and then they were, you know, unveiled their geometric structure. Now there is another geometry which is much more interesting. It started as purely German prose without a single formula and a single model. It was proposed as the Geometrie der Wirklichkeit, die natürliche Geometrie, and so on, by Johannes Hjelmslev in 1915 in Acta Mathematica. In fact, the only paper having anything to do with the foundations of geometry that ever appeared in Acta Mathematica, and in 1923 in the Abhandlungen from Hamburg. They were followed by a series of papers with a group theoretic axiomatization for a geometry with orthogonality and reflection, where there may be more than one line joining 2 points. Poetically speaking, this is something like mia vita te non chiedo lineamenti fissi, volti plausibili o possessi, as Eugenio Montale wrote in Ossi di Seppia. So what is the main idea of this geometry that appeared as prose? Well, the idea is that when you actually draw something, this is why it's the geometry of reality, that Wirklichkeit, natural geometry, is that when you're drawing a line, if the points are close together, you're not going to be able to draw it the same time the second time. And points have dimension. So things are, you know, are fuzzy, they're not exact. The things that Euclidean geometry tells us that two lines have just one intersection and that a circle is tangent with a line in just one point, makes no sense. If the circle has a small radius, then it certainly has a segment in common with your tangent. So this is the kind of thing that is in those original papers until he gets to do something with them. Now, this kind of geometry has been assiduously axiomatized in all settings: affine, projective, Euclidean, Möbius, Laguerre, everything that you heard so far exists in a Hjelmslev version. So the axiomatizations are due to Klingenberg, Benz, Leisner, Lorimer, František, Mahalar, Rado, and Rodo and Faulkner. The accent on Rodo is wrong. It should be on the O. Connected to this is a geometry proposed by Pambuccian in 1940. He looked at from an algebraic point of view. He said, well, let's look at projective geometry, and instead of making it over a skew field, in other words, over a non-commutative field, why don't we drop a bit the requirements and just say that it's a ring? A ring meaning you don't have multiplicative inverses necessarily. So it's not true that everything that's not zero has a multiplicative inverse. So that you can, for any A that's not zero, you find a B such that A times B is 1. So you try to see how far you can go with that. How does the geometry over something like this look like? And it turned out that to avoid what he called geometric teratology, so monstrosity, you need to restrict the rings to what he called set rings, because those were, he wrote in German, now they're called C rings, that have the property that if A times B is 1, then B times A is 1 as well. It turns that these projective or affine geometries are examples of geometries with neighborhood relations, more general than those of Hjelmslev or Klingenberg. So in other words, although he didn't refer at all to Klingenberg with this analysis, it turns out that they are also those kinds of geometries which are try to emulate the geometry of reality. The difference is in these Bachmann ones, you don't go to the, you don't have orthogonality, you don't have the metric structure. So just projective or affine. Werner Leisner in 1975 axiomatized them in a sequence of 2 very nice papers. Now, Gilbert, in his lectures on the foundations of geometry, asked certain questions. It turns out that those questions were precisely what a lot of the later foundations of geometry will be doing, although these questions weren't published at the time. So, and it's not necessarily that he communicated it to, I mean, it's not through oral kind of dissemination that it came to be so. The questions are, is this art provable with the help of the congruence axioms alone? So the congruence axioms are those in his Grundlagen der Geometrie, basically trivial stuff, together with you can move a segment and the side angle side congruence theorem for triangles. Can you get this arg out of those? Or does Pappus follow from the congruence axioms together with this arg? Or does Pappus follow from the congruent, does Desargues follow from the congruence axioms in Pappus? Prove Pappus and Desargues in the planes based only on the axioms of group 1, 2, and 3, so basically absolute geometry. He says Pappus arises by the elimination of the congruence axioms. Indeed, Pappus is the sufficient condition that ensures that a definition of congruence is possible. And he says that Desargues must hold if a plane is to be a part of space. Is the converse true? So if I have a Desarguian plane, can I extend it to space? All of these are answered in due time. Pappus alone does imply Desargues, as shown by Hessenberg in 1905. Moreover, Pappus somewhere implies Pappus everywhere. If you have it, for example, for two fixed lines, the P's and the Q's, if you remember from early on, there were two lines on which there was 3 P's and 3 Q's. Well, if these two lines are just fixed, then, and the Pappus is true for whatever the P's and the Q's are, then the Pappus is true everywhere. Shown by Günther Pickett in 59. If it is true on the fixed oval, oval being a notion precisely defined, so you think now, instead of the two fixed lines, think of the two fixed lines being made into something oval. If it holds on it, usually it's called Pascal in that case, then it holds in full generality, was what Buchenhout showed in 1966. And Pappus is indeed provable with much less than the congruence axioms Gilbert had in mind. And here we have again Johannes Hjelmslev. In 1907, he analyzed the consequences of some postulates of reflection. This wasn't completely new. Hermann Wiener, that we heard about a while ago, also did some work on reflections, but the depth to which Hjelmslev got was absolutely remarkable. And as I said, he started in 1907 with a paper in the Mathematische Annalen, and then there was a long sequence of papers published in an obscure Danish place between 1929 and 1949. By the way, the fact that I'm pronouncing Hjelmslev is not in honor of Italy, which thinks that the H shouldn't exist. In Danish, you don't pronounce the H, right? So in this case. So his investigations led to an axiom system by Arnold Schmidt that was later simplified by Friedrich Bachmann for a bare bones geometry of incidence and orthogonality, which lies at the heart of classical geometries, which is Euclidean, hyperbolic, and elliptic. In 26, in an afterword to the second edition of Pasch's Vorlesungen, Max Dehn wrote, Hjelmslev's result represents the highest point reached by modern mathematics going beyond Euclid in setting up elementary geometry in the plane with assumptions only regarding a limited part of the plane. Without continuity, one lays the foundations for analytic geometry. In other words, one gets Pappus, and with Pappus, one gets the field structure, the commutative field structure. So this is a remarkable achievement that is completely ignored by most mathematicians today. What are the axioms for these metric planes? This is the only thing I give you axioms for, because of its significant importance and because it's really simple to show them. There are at least 2 points. For every 2 points, there is exactly one line incident with them. If A is orthogonal to B, then B is orthogonal to A. Orthogonal lines intersect. Through every point, there is to every line L a perpendicular, which is unique if P is incident with the line. So you're allowing for several perpendiculars from the point to a line to exist if the point is outside, like you would have in elliptic geometry. To every line, there is at least one reflection in that line. And this is the most important, the so-called three-reflection theorem. It says the composition of reflections in three lines A, B, C that have a point in common or that have a perpendicular in common is a reflection in some line D. That's all. With this, you can do an enormous amount of things. What can you do with it? For example, you can prove the concurrency of the three medians of a triangle. The proof, if you were to go from the axioms, would run probably some 7 pages at least. And requires an enormous amount of creativity. I mean, it's not something that if you just think long about it, you could do it. No. So why would you want to do this? Because it reveals the true reasons why these are concurrent. We know the Euclidean proof, which is easily remembered. The only thing is it obscures the true reasons why it's true, because it uses essentially things that are true only in the Euclidean case. So in other words, you're using absolutely the wrong things to prove it. Pappus holds not just in metric planes, but even in a weakening of this axiom system proposed by Sperner, who wanted to just get des arcs. But it turned out, as was shown later, that you get Pappus as well. This reflection approach has been used with great success in the affine setting, in the Möbius, Laguerre, etc. It has probably generated the largest part in the literature on the axiomatic foundations of geometry. So if you look at the bibliography in this book that I don't know when it will be published, and you count the things that have something to do with reflection geometry and this, then there's probably a majority of them. They're more than half. One of the major successes of this has been the algebraic characterizations of the models of absolute geometry by Bachmann student Wolfgang Pejas in 1961. The configuration theorems of des arcs and Pappus times created an enormous literature by weakening des arcs. There is an enormous literature on configuration theorems. There is Reidemeister, Thomson, Ruth Mufang. There is a surprising development of abstract algebra that goes in parallel with the geometric development. For example, Ruth Mufang showed that if you restrict des arcs, then you get algebraic structures where associativity disappears. You're left with so-called alternative division rings. Alternative means that instead of full associativity, you just have this kind of associativity. A classification of projective planes by the richness of their internal transitivities has been proposed by Hanfried Lenz and fine-tuned by Adriano Barlotti in the 50s and 60s. Whatever happened to the Italian approach? I mean, the stuff that happened right after Pasch. Well, here is the reply that Klein gave to Chieri, who asked whether the Mathematische Annalen would publish a survey of his work in the foundations of geometry. My general experience tells me that papers that are written in that symbolism, at least in Germany, find practically no readers. For they encounter from the start rejection. This has been the case ever since, regardless of country. So I know that even one of the writer of a book in the foundations of geometry has told me that he doesn't read papers that have quantifiers. This is a famous mathematician, by the way. So who did still write in this manner, even though the Boeotians were present and active. Besides Pieri, there is Alfred Taske, who is not afraid of being ignored. And James Smith, a student of Haragauri Narayan Gupta, who was the only student of Alfred Taske, the only doctoral student of Alfred Taske to remain in the North American continent and to study the foundations of geometry. So James Smith was asked by Taske, who was present in Regina, where Smith defended his thesis, where did this field begin? This field meaning the axiomatic foundations of geometry. And Smith answered that it started with Hilbert's Grundlagen der Geometrie. Taske disagreed and suggested that he should be studying Pieri. So, what are the goals of this logically oriented school? For example, mathematical questions regarding finite axiomatizability, decidability, completeness, all of these were addressed by Taske, Rautenberg, Martin Ziegler. Questions regarding dependence and independence of axioms, the hardest of which turned out to be Pasch's axiom, which was published by Leslau Szczerba in 1970. Axiomatizations in certain very simple languages. So the question of simple languages for these that started with Pieri, who had just one primitive notion, this of equidistance, but going just from here, AB congruent to AC, right? So you have a ternary relation, and that's with just that ternary relation, can you say everything in geometry? So dependence and independence of notions, because then you have to show that every other notion in Euclidean geometry can be defined in terms of these. Then you can go into what kind of definitions. What is the quantifier complexity of defining this notion in terms of that? Menger and his students, Karl Menger and his students at Notre Dame between 1938 and 44, proved that hyperbolic geometry can be axiomatized in terms of points and lines as variables and incidents as the only primitive notion. Questions regarding quantifier complexity of certain axiom system in a certain language, the number of variables required for axiomatization. Questions regarding the number of times an axiom must be used in the proof of a certain theorem. For example, all the proofs that we know of Pappus implies Desart use Pappus 3 times. Well, can you show that it can't be less than that? Automatic proof checking and proving, which is of a more recent date. And there's a school in Strasbourg. Julien Narboux, Pierre Dupri, Pascal Schreck, and Michael Beeson from San Jose State University have embarked on a project of proof-checking major results in the axiomatic foundations of geometry, all the way from Euclid to Tarski. Intuitionistic axiomatizations of various geometries that started with Heiting, then Lombard and Wesley, von Plato, Mandelke, and Beeson. Reverse geometry. What are minimal assumptions that are needed to prove a certain result? For example, Barbilian in 36 asked for those minimal requirements needed for the truth of the following statements. The segments joining from a point in a plane of an equilateral triangle. You join the point with the vertices of the triangle. Well, then these three satisfy the non-strict triangle inequality. What do you need for this to be true? And many more were to follow. Now, I'm moving on to the human part of this. I mean, mathematics doesn't happen in a vacuum. It's about humans and about their relations in the communities they're in. First of all, I mean, I'm trying to explain its demise, because today we can say that it's dead. I mean, yeah, it's still alive in me and so, but that doesn't mean that it's not dead. I mean, there's also languages that are dead, although there's some people who speak it, like I speak Western Armenian, but this is considered to be a dead language because nobody learns it anymore. So, the axiomatic foundations of geometry remained restricted, with a Polish exception, which was due to Taske, and Taske had Banda Śmielew as a student. Banda Śmielew went back to Warsaw, and so there was a school there, to the lands where it first flourished, Germany and the German-speaking part of Central and Eastern Europe and Italy. The American postulate theorists, Huntington, Moore, Veblen, and so on, did very narrow work of a purely logical nature on order, mostly between 1902 and 1942. It didn't get any roots in there. Among the great powers of mathematics, the axiomatic foundations of geometry proved to be profoundly unpopular in most powerful centers. In France, it was kind of treated not very welcomely by Poincaré. Then Dieudonné said that all of Euclid is trash, and the only French mathematicians who dealt with this were Léonce Lisieux and Jean-Claude Petit, who were from centers outside Paris, which means in France that it's hardly anything, given its centralization. And they were completely marginalized in their own places. In Russia, Soviet Union, it wasn't considered of any interest for several reasons. Some ideological, some because it just, all of logic, first of all, wasn't good because it was idealistic and Western and whatever. And then in Japan, it didn't do anything. In Great Britain, it hardly did anything. And in the United States also, nothing. So there you see already a problem. Another thing changed as well. The profile of what it was to be a mathematician radically changed between the beginning of the 20th century and later times. The generation that was educated before World War II looked at mathematics as one among other things they were interested in. And they did it because they were curious, not because, you know, some important people told them to do them to get some prize or something. They couldn't care less about the social acceptance of what they were doing. And they did things in several areas. Like, for example, Max Dehn, Reidemeister, Emil Artin, van der Waals, Sperner. They're known by mathematicians for their work in other areas. Because they were known in other areas, they got some influence over, you know, journals and places. So you could publish things in, say, the Mathematische Annalen or the Mathematische Zeitschrift, because there used to be these kinds of people. This became impossible in the last paper published in the Zeitschrift that was about the axiomatic foundations of geometry was in 1977 or 8. This made it necessary that, because you couldn't publish it basically anywhere, this made it necessary to found 2 new journals. One is the Journal of Geometry, the other Geometria Dedicata, in which this stuff could be published. Because usually a journal that was considered to be mainstream mathematics wouldn't accept this stuff. This stuff was like, you know, graph theory This is not what we consider the mainstream. So, and so the type of mathematician that came later is very different from the original ones. And I put here a quote by Wilhelm von Humboldt to give you an idea of why they were different. Wilhelm von Humboldt created the kind of idea of Kulturmensch, that you need to know things outside of your narrow thing. And this is what he wrote in his letter to Friedrich Wilhelm III, if I'm not mistaken, the King of Prussia at the time, that there is a certain cultivation of the mind and character that nobody can afford to be without. And so this idea got into disrepute. The idea that, you should know, Greek and Latin and literature and music and so on. What are they good for? They're not good for anything. So in mathematics, these things are, I'm not making it up that these people that I mentioned before, and Dane, Reidemeister, and so on, that they're dramatically different from mathematicians today. For example, Max Dehn ended up in the United States because he was Jewish. And he ended up at Black Mountain College. He was the only mathematician there. The people there were poets and painters, artists. And what did he teach them? Well, he taught them, Greek, Latin, philosophy, Italian. Try to do this with a mathematician today. So Kurt Reidemeister, not only did he work in, topology and the foundations of geometry and many other things, but he wrote philosophical tracts against Heidegger's existentialism. Try this today. You have Emil Artin. Emil Artin went with a group of Wandervögel to Iceland on a budget of hardly anything, and they slept in the hay and played instruments to be allowed to be given some breakfast. And he played instruments very well. So this was, this was how it was. It's not that way anymore. So these people were doing, they were interested in these things per loro diletto. That was what they were in. This is not the way you do it now. You do it because, you go to important people who tell you to do this, and the important people say that this is trash, so you're not going to do that. So this change, after this generation, the people who produced PhD students were largely in Germany, and they were in 3 places. They were in Hamburg, they were in Kiel, and they were in Technische Universität München. It's mostly from Walter Benz, from Friedrich Bachmann, and from Helmut Katzel that came students. After the war, Germany founded many new universities, so there were many places where they needed professors. So a generation that ended up with PhDs in the 60s and so did find employment. But their students didn't find any more, and they were criticized inside Germany for not being very productive, although I doubt that if they had been 10 times more productive, the foundations of geometry would have turned out differently. The reason is, first is the mathematicians don't care about foundations. So the question is, okay, it was clear that they're not going to be accepted by mathematicians because you can be completely ignorant of the axiomatic foundations of geometry and do great stuff in your things. In other words, a differential geometer or somebody doing low dimensional topology or PDEs or whatever they're doing, the big people, the important guys, they can be completely ignorant of this and work great with that. And so it is something that is just like, say, graph theory or so. It's a thing that has nothing to do with the mainstream of mathematics. So the other question is, why did mathematical logic abandon them? After all, mathematical logic is also an ostracized version of mathematics. They are also shrinking. Fewer and fewer universities have chairs of it. So why did they not accept this? Well, because they consider it to be something very specific. In other words, logic is supposed to be about universal things, Arithmetic, which you get by just knowing 1, 2, you get arithmetic. Set theory, which is, well, the most general thing. And then you have, recursion theory comes out of this. Model theory tries to beat the algebraic geometrists at their own game. So that's what, modern, it's a proof theory, recursion theory, model theory, and set theory. And what else? There's nothing, because geometry is considered too elementary and not macho enough. These guys are using forcing and things, and you do what? You just prove elementary things? What's that? It's not good. So all of these, so mathematics has moved to, whether it's mathematical logic and so, to demonstrations of certain virtuosity. Musically speaking, they like to out Paganini, Don't give me Eric Satie and that kind of stuff, or some Barcarolle or some Nocturne. These are how many notes can you play per second and how fast? And in that sense, what do we have in the math? What is the big theory that you need to know for this? Well, there's nothing. It's just a little bit of 19th century geometry, which everybody doesn't know. So you don't have this kind of, how many books do you have to have read to even understand what it's about? Well, there are not that many. So you can't keep up with the, sophisticated people. So this is why it went down. It didn't have the international stuff. Mathematics moved into a very technical and virtuosity displaying area. And logic, which was a possible home for it, didn't accept them because, well, they're too simple. And they destroy the reputation of complexity that they have. Which means that today, for example, in Germany, where there was all this, there's just one person that is in Hamburg, where Benz used to be, that does foundations of geometry. That is not retired. And there are no students. So this is the end of it. In Poland, there are about 3 or 4 who are doing the foundations of geometry. In the United States, there is Michael Beeson, who is retired for a long time, and me, that's it. And in Italy, there is Silvia Pianta and Eva Ferrara Dentice. That's about it. This is certainly going to die out, and it's institutional. That's what was intended. It's not dying out because the problems are all solved or something like this. Not at all. So that's the thing. And by the way, the places where geometry used to be flourishing in Germany, for example, Erlangen, which had Felix Klein, which had von Staudt and then Strambach, Now the department split into two. One is in some kind of pure mathematics and the other is of data science. All the places that used to have somebody who did geometry, now they do computer-aided design or some kind of thing that is completely unrelated. And is unrelated to anything that happened in Germany. The idea being also that everybody likes to do what everybody else does. So the idea that you're doing something that is purely German was looked badly upon. Because there must be something wrong because the others don't want to do it. So it's better to get a result a few years before somebody in the US would do it than to follow a direction that nobody does. Although without you, this wouldn't exist in the universe. That's it.
Okay, we have a time for questions. I don't know if there are some questions in the chat. Okay. No. Questions? Clarifications or? Vincenzo, please.
Something before, thank you very much for your wonderful presentation, very clear, very easy to follow, using beautiful experience to stay here and listen to your conference about geometry, and also very fascinating in the sense that you put in your presentation a lot of emotion for your event. So this is wonderful for us. Thank you very much. I have a feeling a bit different from your about all this stuff. First point, already in mathematics, this aspect is agonistic and ludic aspect of mathematics was present. Think for instance, to the 10th book of Euclidean elements. This is a book in which the technicality is very, very high. It is very difficult to follow also for us today. Because there was a sort of pleasure by people, like Euclid and his friends, in arriving at the level of abstraction, even if the context is much smaller than ours. The technicality was enormous already. So it is something typical of mathematics to follow the mainstream and arriving at the highest level of the mainstream. So it is not something typical of last century. It is something typical of mathematics. The same holds not for Archimedes, who was extremely agonistic and look for complication and something. The general attitude, he was a virtuoso of mathematics, and he showed all his virtuosity to his colleague around the Mediterranean. There is a surge of this kind, so it is typical of this nerve mentality of mathematicians all the time in the place. This is the first observation. Second observation, I have the feeling that you spoke above all about axiomatization through mathematical logic. And I remember my formation was fundamentals, this book by Taske of 1978 that we didn't quote. It was a fundamental moment in the history of axiomatization because Taske was the old generation, Soup is the new one, and I was torment the idea of Minkowski is that to axiomatize is not a logical question, it's a set theory question. So, because set theory is much more powerful than mathematical logic in axiomatizing, and so in a certain sense, I am very favorable that the biodiversity approach to mathematics, and you are right in saying that we have a mozzarella effect, in the sense that people make all the same thing. A scholar that go inside the community, scientific community, make exactly what all people make. The man by Heidegger. People make what all people make without, and on the contrary, as a historian of mathematics, staff scholar of the foundation of mathematics, philosopher of science, we must protect biodiversity. So it is a pity if no one will follow the kind of approach that you say about the foundation of geometry. But at the same time, I have to say that there is sometimes there is a reason because people resist the mainstream. Here the reason is the set theory is much more powerful, and all mathematicians will say that to continue to axiomatize theories with mathematical logic is not so interesting or better. You have to give to me a philosophical and epistemological reason why it is better to use a weaker instrument than a more powerful one. Because set theory is something that gives us a lot of different possibilities that mathematical logic cannot give to us. Perhaps one can say that the meta theorems in mathematical logic are much more controlled than the set theory. There are reasons, but in general, when something is a mainstream, there is in mathematics, in physics, in science, there is a reason. No? It's not something completely casual. So I understand the importance of our approach, our aim to protect the biodiversity of research, but at the same time, I think one have to accept that set theory is so important. I remember this sentence by Euclid, for me was very important. The language of philosophy is not mathematical, it's set theory.
Yes, it's very interesting. You're absolutely right. I mean, the question is now, I'm not a Hegelian. I don't think that the direction of human history reveals some deep truth. This may have to do with my upbringing, with the things that I've seen in history and so on. I'm not an optimist. I don't think that it's going in any right direction. So the fact that something is fashionable or that the important people say it is so doesn't matter anything for me. Now, I certainly think that there is some reason for all this. And you're saying set theory to start with this, you know. Why don't we accept the description of geometries? I mean, if you try to publish something in a paper, in a journal that is serious, then you don't start with axioms, and for God's sake, don't put any quantifier or formal symbols in it. Okay? That's for sure. And you say, let this be a structure and let me be characterized by these properties. That's acceptable speech in the good society. The only problem is that the people who publish these kinds of things, their things get to me as reviewer at Centralblatt or Math Reviews. And the people who publish this in the top places just repeat in that language weaker versions of the things that were known by the foundations of geometry community. And they get published because of the general ignorance of anything that I'm speaking about. So this comes at a price. I mean, the idea that one is proud of not knowing anything about the foundations of geometry, I mean, the big shots are thinking in that term. For example, Arnold, when he retired, he wrote a paper saying that the concurrency of the altitudes of a triangle has something to do with the Jacobi identity in Lie algebras. Well, this sounds very good because in mathematics, it's considered that you're very smart if you connect two disparate fields. The only thing is, this was very well known to not be the case. In fact, Friedrich Bachmann and Hjelmslev had resolved the problem long time ago, and they have absolutely nothing to do with the Jacobi identity or the algebras. In fact, they don't, you can do this without any algebraic system to be available there. In other words, you can do it in a system which can't be coordinatized with anything. This stuff gets published if you write these kinds of things. There's a guy who wrote stuff about constructibility in the hyperbolic geometry and so on in the Mathematics magazine that said only nonsense. In other words, thought that things were not known that were known from 1927 from Mordechai Bolzowski. And the paper got the prize for the best paper in the Mathematics magazine for that year. So, yeah, I mean, you can write in that tradition and be sure of success. If you want to write a paper that will be published in the mainstream journals, you can skip a whole century of the foundations of geometry, refer to Gilbert as if it were the dernier cri, and you get published. There is no other field in mathematics where you can do that. You can't get a paper published in the Journal of Group Theory by referring to Silov and saying this is the last, the dernier cri, and I'm making now an advancement. So why not base it on this description of set theory? Because set theory is fraught with a lot of problems. And you want geometry to be outside of this if possible. So the question is, yeah, you can do it with set theory. And nobody says you shouldn't be doing algebraic geometry or differential geometry. The question is rather, what part of these is purely geometric or elementary geometry? And this concern doesn't come just from the axiomaticians. Herbert Busemann had a similar concern. Why do we need differentiability in geometry? Can't we do it with just continuity or fewer requirements? And it turned out that yes, you can do it. He was also ignored for most of his life. Later on, the differential geometers discovered him. In particular, Russian geometers liked this thing. Alexandrov did the same thing. So the idea of moving away from unnecessary stuff is also a movement in mathematics. And you're right, the other question is, should we play lots of notes per second? I mean, the kind of, the thing you mentioned, that virtuosity was always considered. That is true. But I'm not saying that this is not virtuosity. What Hjelmslev did is incredible as virtuosity. The thing that is not appreciated is the fact that these do not use some kind of machinery that is out there. So this is pretty much like Novikov and Adian proving the Burnside problem. There's no theory in it. It's just pages after pages after pages of an incredible induction argument. Okay? So this isn't considered good. Good is considered to use heavy machinery, nuclear weapons, that kind of thing. The axiomatic foundations of geometry is seen as pedestrian. You're not using, you know, machinery. You don't show that you're a person of the modern world. You go just by your own, and that's it. You go on a path. Other people have planes and helicopters, and you're going like a stupid guy. What's this? This is something like a Luddite. You're against technology. You're defying your century and your advances. So it is something very deep. I mean, do you believe in this or that? And as you're saying, I don't think that anybody in the foundations of geometry thinks that the PDE people should stop doing PDEs. The question is whether this deserves the right to exist. Yes. And mathematics has decided, the mathematical village has collectively decided that it does not. And the reasons were that, first of all, they don't understand any of this because there is no geometric education in existence today. In other words, the typical mathematician has zero knowledge of geometry. There was none in high school. There is none at the university, except for something that is some linear algebra nonsense. So there is no true geometry. So in fact, these people speak a language that is completely incomprehensible to the regular mathematician. And there are two things if something is incomprehensible to you. You either say, I don't understand it, but it might be something, or you say it's trash because I don't understand it, because obviously I'm a very important person. So if I don't understand that, it must be something wrong. And that's what the village has decided.
My secondary school teacher of mathematics, she was a wonderful teacher. She preferred always geometric proof without mathematics. But there was something for her was very, very important. But so all our pupils look for proofs that do not use geometry, do not use algebra to solve the problem. Yeah, and many mathematicians have, I think, also many mathematicians have this feeling for that geometry. It's not completely that, I don't know. For instance, I'm also Roberto Macari, our pupil, learned very much. They don't know if they can follow his following Macari Roberto also knows very much this kind of synthetic.
I don't see him here, yeah.
So you're right. Thank you very much for your.
You're most welcome.
I don't know if a question or online. Question in the chat. Okay, this is the question.
Okay. What had Felix Klein said on the question, what is geometry and influence on the axiomatic foundations?
No.
Yeah, so the question is if Klein's Erlangen, yeah, sure it had an influence, but I would say that several of these definability questions among notions have a whole lot to do with a modern version of Klein, because Klein said, well, a notion is geometric if it is preserved by a certain group of transformations. And in this has a logical equivalent in definability. You can say this notion can be defined in those terms. So one can say that in this sense, we have a continuation of Klein, and certainly all of the geometry of reflections is nothing but Klein. So yes, that is an enormous influence of Klein. In fact, not only Bachmann was influenced by this, but Walter Benz is certainly in that tradition. In fact, his doctoral advisor was a student of Klein and New Klein. So I think that, yeah, there is but I think that is mostly ignored, because today I think that respectable geometry is either some, I mean, I know when I was at Michigan, the people who wrote that they were doing geometry without any adjective were actually doing three-dimensional manifolds with some geometries on it. Or they were doing low-dimensional topology or so. Yeah? Okay. So to say that you're doing geometry without any kind of other things, that you're doing just the 51 classification of geometry, was considered something absurd, because you have to use some additional stuff. This is like doing it a cappella, you know. Why should you? You should invite an orchestra.
Yes, Rafael, please.
Yes, Rafael.
Okay, it's me. So I have one question related, you know, to something which is quite interesting for me in the foundations of geometry. When you talked about different traditions in geometry, there is one more tradition which relates to some alternative foundations, like solid-based geometries of Taske, for example, and Jaśkowski.
Yes, I forgot to mention those.
Yes, there is also, yeah, but this is not a comment. I would like to ask a question. There is also your systems, very interesting, which has a reflection as a basic notion, yeah, which are actually a system of geometry which are based on some movement. So my question is, whether do you think these are important branches of foundations of geometry, and do you think they can influence somehow development of foundations of geometry in the future?
Yeah, the mereological part, the part all the Lesniewski, Taske, and so on, tradition in Huntington. The problem there I see is that nobody has succeeded in finding an elementary axiomatization for it. I mean, there's you need a little bit of higher order things to make things work. If you go for just any body, I mean, if you go for spheres or nice bodies, you can do it in a first order setting. Else, it's not possible, and that I think makes it not that elementary. It is an axiomatization, obviously, but it's not an elementary one. The other things, reflection and so all of this stuff, as I said, the problem is with them, with acceptance, is that they're elementary, and people don't like elementary things. I mean, people, the important people. So in a certain sense, you can't have it all, you know. I mean, the thing with the bad thing with geometry for logicians, let's say, is that unlike arithmetic, which is essentially undecidable, all of these geometries have a decidable and complete extension. I mean, you add this first order continuity axiom the way Taske does it, and you get this you know, complete and decidable theory. So logicians are consider that this stuff is not interesting. You can't do this with arithmetic, which is why it's interesting, which is why you have degrees of unsolvability, and recursion theory makes all that sense. So you can't compete with that on a logical side. On a mathematical side, you can't compete with the with the differential geometry people or with the algebraic geometry people. So it's hard to, the issue is hard to resolve because it's a question of aesthetics mostly. I mean, a mathematician who looks at Bachmann's achievement, for example, says, well, what is this? These are O3KF. These are orthogonal groups over some commutative fields with a ternary form. So what's that? That's something not that interesting. But, so what Bachmann does is to find a very concise poem that generates everything that's true in there. Now, this is something aesthetical. Do you care for this? The community of mathematicians has decided, no, we don't. It's enough for us to tell me what the group is, and I say, okay, that's a group, and it's fine. I don't care about the, finding an extremely condensed version of telling me what are all the things true in there, or how I can found that. So the idea of foundation, of beautiful foundations of these theories is not something that is mainstream.
Yes, but if I may, one more remark, but you can also have a look upon these alternative foundations which take a different ontological basis, also as a kind of a reverse geometry, as I can see it, because you can ask yourself a question: what logical and mathematical machinery do I need for this ontological basis to develop some system of geometry? And yes, this for me seems to be very interesting, very stimulating, and often leads to very, very highly aesthetical results. This is how I can see it.
Yes.
This is what in my eyes justifies the work in the higher order foundations of geometry in a way. Yes. I don't know what you think about it.
Yeah, I'm sure it does. I haven't, as I said, to me, it's very interesting. And I think that all of mathematics is interested in fewer assumptions, the way you're saying, right? A minimal basis for something, yeah? The only thing is that the question is, in what direction does mathematics go? The Greek direction was to find this minimal thing. There is a more barbarian version that says, I don't care the minimal thing. The outside environment satisfies all of these things. Why do I need to minimize myself to the minimum? And the barbarians won the day. I mean, we're not in ancient Greece anymore. There are no philosophers to tell you, this is how it has to be done. So people do whatever, and plus mathematics has to be useful. I mean, you have to explain why it's good. Islamic mathematicians explain that it's good because it tells you how to where Mecca is and what the days are and so on. We have to explain our existence by saying that it's useful for something, medicine, weapons, whatever. And the question is, how is this good to say that, I can do it with fewer things than more? I mean, if I can do it in Euclidean geometry over the reals, why should I do it with just so many fewer things? This is like going, like walking when you have, trains and planes and things. And people are proud of these things, of planes and smartphones and so on. You don't use them, that's not good. So you understand what I'm saying? It's something about your values. It's not something that you can, and values are kind of at a subliminal level. I mean, you're not even aware of them, and you judge with them. And there is another comment I've seen right now.
Okay, thank you.
Yes.
Thank you.
Yeah, thanks. Yes, yes, Valentin, sure. You're right. I mean, the question of the future hasn't been settled yet. And Michael Beeson wrote a preface to Schwabhäuser, Hjelmslev, and Taske, the Metamathematische Methoden in der Geometrie, which was reissued by Ishi Press, in which he writes that the readership of this book, which is profoundly axiomatics of geometry in a very logical setting, the majority of them haven't been even born yet, because 500 years from now, there will be a small minority of people interested in points, lines, triangles, and so on. And so, yes, you can look at it this way. I have no looking glass into the far future. I'm just saying that in the current environment in which you learn something as a graduate student, you get a PhD thesis, and then you do some research in that, that has been broken. There is no continuation of that. Which doesn't mean that people individually and on their own cannot pick up the literature and do this. They won't get any jobs, that's for sure. But they can do it, or people retired can start doing this, or people who don't care about, they are already tenured, they can do this. But I'm just thinking about the sociological setup is in fact discouraging you from doing that, because there are severe punishments for those who will do that. Yes. Yes, yes, please. Oh, I have to do something, right? No, I don't have to do anything. Okay.
Can I talk now?
Yes, definitely. And we were hearing you. Yes.
Thank you very much once again. It was really a very enjoyable talk, and I look forward to the rest. So I fully agree with you, and I can fully understand your frustration. But if I may offer some consolation, it comes from history of logic.
Yes.
Because you surely know well, since the time of Aristotle up until the early 19th century, logic was, well, not even dormant. It was, well, pretty much, let's say, almost non-existent.
Yes.
All of a sudden, it came up again, and then it's flourishing now. And well, who knows about the future? But maybe some centuries or more after us, foundations of geometry will become the fashion of the day again. So,
yes, no, absolutely, absolutely. The farther future is definitely unknown. I'm concerned about the immediate future. A certain break, like the fact that, for example, now nobody can learn projective geometry from somebody with a lineage that goes back to the 19th century. Like there are people, you know, who learn piano from somebody who learned from somebody who will go back to Liszt or something, right? Or Rachmaninoff or who knows what, you know? Well, there won't be this. There is no one today who can learn projective geometry from somebody, you know, like it used to be, you know, Beniamino Segre or somebody who actually knew it in a certain way, because there is knowledge that is not in books, that is alive somewhere. And this alive tradition will not exist. People will need to learn this the way we learn about hieroglyphs, you know. It is in books, but it's not a living tradition. It's dead for all practical purposes. And whether it's sad or not, I don't know. I mean, there are all kinds of biodiversity disappearances, so I don't think that that's the most important. You know, it's not an existential matter for humanity. But yes, we don't know what the longer future has in hold. As I say, the 500 years that Beeson speaks of, I don't know about that.
Okay, we have time for just one last question.
Yes.
Question? Vincenzo? Again. At a certain point, you said something that struck me very much about the fact that in a certain moment in Gilbert's perspective, he looked for axiomatization of geometry because his problem was which property must have geometrical figures to respect certain algebraic properties. Have I understood well?
Yes.
Because this is very interesting because I was very interested in the problem posed by many scholars about what we regard in general representation theorems.
Yes.
In the sense, for instance, definability, savage, Supis, all tend to understand which must be the general properties of the sample space in order to build not a unique but a reasonable measure of probability respecting homomorph axiom. And this is a question that is not, it is another question that today is not so studied, also in epistemology, where would be very, very important because all people use without problems theory of probability to make epistemology without posing this question. And it seems to me very similar, and people like these guys, Savage, Definity, and Supis, ask for this kind of question that is deeply fundamental in a certain sense. It seems to me something similar to what was the reason for Gilbert to axiomatize geometry, and also something similar to what did von Neumann in axiomatizing game theory, the moment that he, not game theory, choice theory, the moment he said, yes, we can use this notion of utility and expected value, but to use this kind of metric, we need that our preferences must respect this set of axioms. And the set of axioms are not always reasonable when you speak about human behavior. So this is a sort of understanding what does it mean to use this formalism, and it seems to me what does it mean to use algebra in making geometry. You must have a kind of geometry that must respect certain qualities, as it is not it is meaningless to use algebra to make geometry.
Yes. Yeah. Yes. So what Hilbert said there is that a mature theory has to arrive to a place where it can introduce number, right? So the idea is we can introduce the typical classroom introduction of affine geometry. Tells you that you have a vector space over a field and you have this and this. Well, Hilbert doesn't like it this way. You shouldn't tell me from the beginning that there is a field and a vector field and all the vector space and so on. The field has to come out of the geometry, right? So you should be able to construct your numbers geometrically. You shouldn't tell me from the beginning that there are numbers in the geometry. So in that sense, in other areas, in probability, it should be the same. It should be the axioms that give me the numbers. I should be able to recover the numbers from the axiom system. And in everything else, it says if it reaches a certain maturity, you should be able to get that. And this is what I call algebra, because obviously your numbers won't be the integers and won't be the real numbers. So there will be some algebraic structure there. Yeah.
Okay. Thank you so much, Victor. And the second lecture is scheduled for March 16, the same time. The title is The Parallel Postulate. And thanks again, and thank you very much to everybody. And okay.